Hello, my name is Justin Kugler. I'm the Vice President of Advanced Programs and Concepts at Maiden Space Incorporated, located here in Jacksonville, Florida. I'm also a longtime board member and supporter of Space School, so I'm really excited to share with all of you the work that we're doing to build the industrial economy in space. This ranges from building parts and equipment for satellites in low Earth orbit, all the way to manufacturing and constructing on the moon, and hopefully eventually Mars and even asteroids. So we're going to start with a brief video on some of the work that we're doing for the lunar surface, and then your instructors will show you another video that I've done on some of the broader technologies, particularly for satellites that we're working on at Maiden Space. And then if you have any questions, I'll be happy to cover those in the Q&A session. With that, we'll go right to it. So the reason why Maiden Space exists is for what we call driving utilization through on-orbit manufacturing. It's a kind of a fancy way of saying that we're focused on what you do when you actually get there. There are a lot of great companies working on lowering the cost of transportation to space. There are a lot of great companies working on figuring out, how to build the next space station, or how to build, plasma rockets to get to destinations in space faster. Whereas we're focused on taking advantage of revolutionary advances in manufacturing technologies to make it easier, cheaper, safer, and more cost-effective to deploy things like functional structures off of small satellites, and for the astronauts to do whatever repairs and servicing they need to do on long-duration missions without having to carry every conceivable part that they could ever imagine that they would need to have. So at Maiden Space, we're focused on what we consider three critical sectors. The first is space exploration solutions. So making it easier for astronauts to live and work in space. And that was really where we got our start. We're also doing a lot of work these days on payload development and operations. So actually figuring out how we can use the low gravity environment on board the space station to make new services, new materials, and new products that not only make it better for the space industry, but actually can be infused into products here on the ground that make your life and my life better and easier. And then where we've seen a lot of growth over the past couple of years is in what we call satellite manufacturing. So actually making it so that satellites can build parts of themselves like antennas and reflectors and solar arrays that are much larger and much more cost effective than what is possible with traditional deployable technologies. So we're about 10 years old. In fact, this is our 10-year anniversary. I've been with the company since 2016, and you can see that every year we've made stepwise progress towards our goals. In 2014, we were the first company alongside our NASA partners to actually make parts off the Earth with our 3D printing zero-G experiment. And then only 2 years later, we launched and flew the first commercial 3D printing facility based on the lessons that we learned with the 3DP experiment. And then also started our Archinaut program with NASA Space Technology Mission Directorate. And those two activities combined are really the core of all of the technologies that we're developing here at Maiden Space, because they're focused on automation and taking advantage of space itself as the build environment to do things that you can't do on the ground. And then last year, we've started taking our Archinaut program to the next level. We're actually building the first satellite that will manufacture and deploy its own solar arrays. So you might ask, how does that lead towards doing work on the moon and doing work on asteroids? Well, it starts with the work that we've done on on-demand part manufacturing, but it also turns out that a lot of those same core technologies and capabilities are useful for things like heavy construction and even regolith printing. So when we talk about on-demand manufacturing, that means being able to make specialty parts at the point of use using the resources and tools that you have on hand. So for example, on the NASA Gateway, we're working with NASA and other companies to have a fully automated, almost assembly line style manufacturing system, so that if you need a replacement part, whether that it needs to be made out of metal or polymer or ceramic or even some hybrid, we can simply upload the CAD file, hit the print job, and then using the robotic tooling that's built into our system, move it off of the assembly platform and into a staging area so that the astronauts can take it when they need it. We're also doing work on what we call robotic heavy lunar construction. So for long duration sustainable missions where we're not sandblasting everybody with debris, we need landing pads, we need berms, we need roads, we need equipment garages. And so we need specialized equipment for the moon and eventually for asteroids that can use local regolith rocks and dirt and as what we call construction aggregate, so that you don't have to carry all that heavy bulk with you to your destination, whether that's the moon or whether that's an asteroid. And so much like the same way we can use, sand or recycled brick or other, local materials for things like concrete and asphalt here on the ground, we want to do the same thing on the moon, Mars, and other destinations. And you can see in these pictures that we're actually already making great strides on that front. We're actually working with NASA Marshall on a regolith printing machine that combines essentially lunar dust with a binder material, so that you can make things out of lunar regolith in much the same way that we make plastic parts on board the space station. And we successfully completed ground demo work last year and are now hard at work on actually building the first flight demo machine that's going to go up to the space station next year to show that we can do it in the low gravity environment as well. So, going forward, we combine all of those fantastic capabilities together. That allows us to, deploy satellites around the moon, Mars, and asteroids that provide high power sensors for imaging and communications. Because as we get further and further from the Earth, those capabilities are going to be critical. And then with these advanced multi-material manufacturing and automation systems, we'll be able to provide on-demand resources to both support the mission objectives and solve critical problems that we weren't able to anticipate, as well as to build the infrastructure and complex structures on the surface that support human exploration and settlement activities. So if you have any questions after you watch this and the next video, please give them to your team leads and your teachers, and I'll be happy to go over them more in the Q&A session. I really look forward to talking with y'all then. Hope y'all are really enjoying Space School, and good luck on your projects. Thank you.
We are doing amazing things here in Jacksonville right now to create that fantastic future that Lee was talking about. And I'm going to show you a little bit about how we're doing that, where we're going, how that fits into what NASA's doing to go back to the moon, and what we think that portends for a future that we can all participate in. Apollo was important because it was a geopolitical battle with the Soviet Union that we thought we could win. And once we won that battle, the program was over. So how do we build something that's sustainable? How do we build something that takes the best of everybody and helps take humanity and American values into the future? Well, if you talk to sociologists or you talk to people like Neil deGrasse Tyson, and they look at history and they say there are three things that have always motivated us in the past: God, gold, and guns. And we're trying to build a better future where we're not shooting at each other, and we already did that in the Cold War, so we're trying to get away from that. And we're trying to build this more inclusive future where we bring the best of everybody, so we don't want to exclude anybody because of what they believe or what they don't believe. So what comes next? And that's economic motivation. That's industrializing space, putting it to work for the benefit of humanity so that we all have a better and brighter future. And that's exactly what we're doing at Made in Space. So when I talk about space industrialization, what do I mean? That means moving the means of production from here on the Earth, on the ground, into space, so that we can generate new value and that we can return that value back to people here on the ground. I've worked in the space program for 15 years now, and people have asked me, why do we do this? It's cool. You build cool technology. You fly people in space, but what does that do for me? So there are three ways that we think we can generate value by industrializing space. The first is what we call exploration manufacturing. So we put the first 3D printer on the space station in 2014. We then followed up with a commercial 3D printer that we actually own and operate as a service for NASA on the space station. We're doing that for 3 years now, where we can actually build parts and tools and whatever the astronauts might need that they didn't think of before they launched, we can make it for them so that they don't have to wait for the next cargo launch to solve a problem. That's increasingly important as we move further and further away from the Earth, because it takes longer and longer to travel those distances. And we don't have the logistics train and resupply that we enjoy even as close as low Earth orbit. And we don't want to have another Apollo 13 situation where we have a scrubber that's one size and a port that's another size, and you have to scrounge to fit the two together. No, our interns can solve that problem with computers and a 3D printer in less than an hour. And we can send those digital files up to 3D printers on the space station so that all the astronaut has to do is take it out of the printer, plop it in place, and go back to whatever it was that they were doing. The second area that we're focused on is what we call space-enabled manufacturing. This is one that's really exciting for me. Before I came to Made in Space, I worked in the space station program in Houston, Texas for the better part of a decade, and we were really focused on figuring out what can we do to take advantage of the microgravity environment where you're in that constant free fall to create new products and services that you can't make here on the ground. At Made in Space, we flew the first fully commercial facility to the space station to make a new product in space that you can then bring back down to the ground and sell here on Earth. We've actually figured out a way to make high-grade optical fiber so that you can make better communications devices, better medical lasers, and actually improve the lives of people here on Earth. And we're working with NASA now to create new facilities for things like high-grade metals so that you have turbine blades that don't break. We're working on optical crystals so that you can create cell phones that never run out of power. And we're doing work on ceramics that can line the insides of turbine engines so that you can get more efficiency and more power and reduce pollution. And there's a whole other slate of stuff that we have coming up in the future. All of that hardware is being built by our team here in Jacksonville and is getting ready to go to the space station over the next year. But the area that we're really excited to talk to you all about tonight is what we call in-space manufacturing and robotic assembly. Everything that we fly to space now, everything over the past 50 years, is all designed to fit on top of a rocket, survive those intense forces, the G-forces, the vibration, the roll program, all of that, to get up there in space and do a job. But because it has to survive that environment and fit inside of a tiny capsule or a payload bay, it puts constraints on what we can fly and how we can fly, and it makes it really expensive to do that. But if we can take advantage of that low gravity, benign environment in space and actually build what we need when we get there, that allows us to create new structures and new space systems that you couldn't even imagine here on the ground. And that includes solar arrays 10 times bigger than what we can make on the ground. And we're talking about antennas that are the size of a football field, something coming out of a package the size of a refrigerator. Whereas today, those things cost hundreds of millions to billions of dollars. And if one thing goes wrong, you're out the mission. But we can actually build those systems, repair them, and sustain them much the same way that we do with terrestrial infrastructure. We're actually getting ready to do that in space for the first time, built from a team here in Jacksonville. We just won a contract from NASA last week, a $74 million program. Thank you. Here in Jacksonville, and with our team in California, we are going to build a satellite and deliver it to NASA that can actually manufacture and assemble its own solar arrays. So as you can see up here, we've got a satellite that's about the size of a dorm fridge. We're starting small because we want to show that we can start small and scale to much larger objects. We have a robotic system that actually uses space itself as the build volume so that we can create structures of almost indefinite size and of varying complexity and shapes. And as that structure is continuously manufactured, it pulls the solar arrays out with it. That's important because that means we don't have to have complicated motors and deployment mechanisms that take up space, volume, and mass and make these systems much more complicated. So off of this small satellite, not much bigger than I am, we'll be able to make solar arrays that are 10 meters on a size. And we're going to do 2 of them off the same satellite. So today, as a point of comparison, see those 3 little white rectangles? That's as big as you can make a solar panel off of that size of a satellite today. So we're talking about something over 10 times the size that can generate more than 5 times as much solar power. That's important because anything that we fly to space, it's power starved, it's power hungry. And that limits the amount of bandwidth that we can send back and forth. And that's important because there are 2 ways that you can make money in space right now. One is by getting NASA government contracts, which we're very grateful for. The other way that you can make money in space is by either generating or relaying ones and zeros, creating information. So that's communications relays, observation satellites, and all of that needs power to operate. And right now, the way you get really big power is by building really big satellites. Really big satellites are really expensive to make. They're really expensive to launch. But if we build it when we get up there, we can do it on smaller, much more affordable satellites. If you can do it on smaller, more affordable satellites, you can use smaller, more affordable, reusable launchers. And that gets you that virtuous cycle where the cost of utilization goes down and the amount of utilization goes up, and that's how you build a sustainable growth economy in space. You might ask, what does that have to do with the moon? And how does all that technology come together? NASA has been charged by the administration with putting people back on the moon by 2024, and they've created the Artemis program, the sister of Apollo, to accomplish that. The reason why we want to do that is because we've learned from the Apollo program that you have to build for sustainability from the beginning. If you look at the history of exploration, it's a very similar paradigm. The first time we went to Antarctica, we essentially did almost throwaway missions. We sent people out on expeditions. A lot of times their ships broke and crews were stranded. But over time, we built up the capability so that now we have permanent stations at the South Pole. We have McMurdo Station that acts as a resupply and continuous operations base. And we're continuously conducting science, engineering, and sustainability research on Antarctica, the last frontier on our planet. Well, with Artemis, we're going to do the same thing on the moon. We're going to go figure out how we can safely land people using commercial landers and infrastructure supported by NASA launches on the Space Launch System that'll be the successor to the grand Saturn V that we saw earlier tonight. We're going to conduct scientific exploration and surveying expeditions so that we can understand where are all the resources. In the gold rush era, was there's gold and then there are hills and in the rivers. To the moon, we're going to go look for water because you need water to sustain human life and to create fuel. We're not going back to the moon this time, just to demonstrate American superiority the way that we did with the Apollo program. We're going back to the moon this time to show how we can use space exploration and development to put space to work for everybody else and use those resources of space to elevate the human condition. And that brings me to really kind of the point behind all of this. And what I was talking about before, people ask me, why do we do this? Why is this important? Yeah, it's cool, but what's the point? So, going back to the picture of the pale blue dot, the only thing that stops Earth from being a closed system, and we know from the laws of thermodynamics that in a closed system, entropy can only increase. The amount of energy that you can use over time only decreases. The only thing that stops the Earth from being a closed system is the input that we get from the sun and the occasional drop of what we call rare earth metals from asteroids on the planetary surface. And in fact, most of the major metal mines for things like platinum group metals today are actually leftover asteroid impact craters because those materials are so heavy that the ones that were naturally present in the Earth all sunk to the core billions of years ago. So the only way that we break that cycle, the only way that we can obtain enough energy to let everybody live in a life of luxury and a life of comfort, and do so in a way that we don't tear up the Earth and destroy our biosphere to do it, is to go to space. We have all the sunlight we could ever need in space. There are asteroids that have more useful metals than have been mined in the entire history of humanity combined are on single asteroids. And so to put space to work, to make a better future for everybody here on Earth, and to do so in such a way that we can have clean air and clean water and pursue our bliss, and do so in such a way that we don't destroy our own society and we don't destroy our own planet, we have to go to space to do that. And to do that, we have to build the tools and the technologies so that we can do the living and working in space and build what we need to get there. I grew up watching Star Trek: The Next Generation. I grew up watching Babylon 5. And now I love to watch the Expanse. And in the far future, once we've built that industrial infrastructure and we've made it affordable for people to live and work in space, then we can go beyond. Then we can conduct human exploration. We can go see Jupiter with our own eyes. We can eventually launch ships to other star systems. And we can build cities in space where people can live and work and continue to grow that human experience. And it's going to be on spaceships that are so big that they can only be made in space.